Okay, welcome to Math 150, Section 1, 2021, Lecture 29. So this is the last of the review sessions. Just put somebody in the waiting room. And so I will start off with the questions that people had already asked, and then if there are other questions you want to see, just let me know. As I mentioned, my kids got their first shots yesterday, so I'm waiting for the email to come in as to when I can schedule the next ones. So when that happens, class will be potentially paused for a few minutes. Okay, so the first question was on LevelSets. And we've seen lots of applications of LevelSets. One of my favorites is with Lagrange multipliers. Is you can view this as we are forced to lie on a level set, g of x, y, z equals 5 or 7 or 0. And we want to find where on that level set does the function take on its largest or smallest value. And we said that what would have to happen is the gradient of f would have to be parallel to the gradient of g for a candidate. That doesn't mean that that's where you win. It just means it's a candidate. It is a potential point that you can check. So level set of the height c is all inputs that evaluate to c. So if we have a function of two variables, it would be all xy such that f of xy equals c. So depending on what function I give you, you will have very different level sets. And the idea is if I plot a level set, it gives you some idea of what a space looks like. So that's 10, let's call that 100. Let's call this 200. Let's call this 300. Let's call this 300. And let's call this 400. What do you think I've just plotted? Does this mean anything to you? Yeah, topography map. And what do you think? Can you tell me anything about the geometry of this space? It looks like there are two peaks, like two mountains, right? And so I've got two places where it's climbing up here. Now, different things could be happening in different places. If I replaced the 100, 200, and 300 with negative, what do you think this might be? It might be an abyss, or maybe it's the water depth, and I'm in some kind of lake and seeing just how deep the water gets in places. But you can get a good sense of what's going on just by looking like that. I'll try to make the picture a little bit larger. So roughly, what is this? Try again. I'm sorry? No, try again. No, this is disgraceful. It's close when you say the United States, but this is not the United States. This is the continental United States, right? 50 states, plus some possessions, territories, and whatnot, okay? So you might get maps that are something like this, where these are maybe temperatures. You've probably seen maps like this, or maps where the pressure of one. So level sets, you see these all the time. And so depending on what function I give you, it's going to be different algebra to find the input. So if I give you, for instance, x squared plus y squared, if that's my function, what can you tell me about the level sets? Yeah, there'll be circles. So what are the possible values of c? If c is okay, so if c is 0, what do we know about the level set? Is a dot. Is just the point 0, 0. What else? What if c is negative? It's okay, so it's empty. And what if c is greater than 0? So what would it be if you got almost square root of C? So circle with radius square root of C centered at 0, 0. So that would be the level set for this function. And the more complicated function I give you, the harder it's going to be to find the level set. It all comes down to doing algebra. So if I give you something like the sine of x squared plus y squared, say we have something like this. What can you tell me about the level set here? Good. So it's empty if the absolute value of C is greater than 1. And then for any C between -1 and 1, you would want x squared plus y squared to be the arc sine of C. So what can you tell me about the level sets? What are they going to look like? So you get x squared plus y squared equals arc sine of C. What is arc sine of C? Where does that live? Well, you've got to be careful because you can always add 2 pi and it's not going to change things. So really, it's not just arc sine of C. It's also plus 2 pi n. So anything like that will work. Now, we need this to be positive, right? Because x squared plus y squared is never negative. So what do you think the level sets will be for a C between -1 and 1? What will it look like? Let's take a specific value. Let's take C equals 1. So what do you want x squared plus y squared to be? What's the arc sine of 1? So we want x squared plus y squared equals pi over 2 plus 2 pi n. So what kind of curves are these? So let's do the case when n equals 0, where x squared plus y squared is pi halves. What kind of curve is that? It's a circle. And let's say it's pi halves plus 2 pi. What kind of curve is that? Circle. And then pi halves plus 4 pi. Circle. It's just going to be a bunch of circles. And we can even figure out what the radius is. The radius would be the square root of pi halves plus 2 pi n. And so that's how you would calculate the level sets for something like this. So again, you always want to break it up into smaller cases. If you're having trouble, choose a specific value of C and try to just work through that. So rather than trying to deal with, well, what does it mean to be arc sine of C plus 2 pi n? Let me choose a value of C and build up some intuition. What's a good choice of C? 1, 0, stuff like that, and try to get a sense of what's going on. And what you'll see is you'll have basically a ring of circles. Does that make sense? Well, if you look at sine, sine is periodic. So every time I increase x squared plus y squared, it's going to have the same value if I increase it by 2 pi. What coordinates might you want to study this in? Polar. And so if you were to plot this in polar, if this is r and this is theta, the level sets would just be lines like that. And they would just be different values of r, depending on this. Any other questions on level sets? So the other question was on interchanging orders of integration. So we have very few techniques to handle multivariable integrals. What techniques do we have? We have change of variables. And again, it is really hard for me to disguise change of variables. Right? If I give you something on a sphere, what should you use? Spherical. If you don't use spherical, almost surely you're making a mistake. Right? If I give you something in the plane and it only depends on x squared plus y squared, and it's integrating over a circle, probably polar coordinates is the way to go. So you need to know the spherical coordinates. You need to know how the volume elements transform. And it's rho squared sine of phi, d rho, d theta, d phi, and for us in the math class, phi is the angle coming down from the z-axis. I have to constantly remind myself I'm not a physicist, because I learned it first from the physicist, where theta is often coming down. So you always have to be careful when you look at different books that you may have different notation. So one technique we have is change of variable. The other one we have is interchanging the order of integration. And this is where the Fubini theorem comes into play. That if you have a nice function, say continuous bounded function on a finite region, then you can interchange the order of integration. And if you do that, frequently one integral is easier than another. If you have an integral of two variables, we have a double integral, how many orderings are there? 2. If you are trying to do an integral on a Calc 3 exam, hypothetically, in the next few days, and you are having trouble with an integral as written, what might be a good thing to try? Sorry? Yes, switching the order, right? And the number of possibilities is small. What if you had an 8-dimensional integral? How many possibilities? Let's do a 10-dimensional integral. How many possibilities would you have? I'm sorry? So how many different ways can I order the 10 integrals? 10 factorial, that's getting pretty large. I think 9 factorial is around 330,000, so this is probably on the order of 3 million. Okay? That's way too much to do by hand and to just explore the 2, that's not bad. So let's do the following. I will integrate 0 to 1, integrate x to 1, e to the y squared divided by. So, given that the preamble for this was discussing interchanging orders of integration, using your wonderful deductive powers, what can you deduce? We should almost surely change the order of integration, right? If you look at this, if I wanted to integrate it with respect to y first, I would need a function whose derivative is e to the y squared. We do not know any function. There is no nice simple function whose derivative is e to the y squared. That's another clue that this can't be the right way to go. So a lot of these problems are really cookbook problems where they are designed to work out beautifully when you interchange the order of integration. And to some extent, that is a hint that you're on the right path. If things all of a sudden start to work out, you're probably moving in the right direction. If things don't, you're almost surely moving in the wrong direction, assuming you haven't made an algebra mistake. That is the difference between an exam homework problem and real life. We are fortunate that there are a lot of problems in real life that can be modeled by nice functions like this. So if we are going to interchange orders of integration, step one is to draw the picture. So when you look at this, the question is, what is the region we are integrating? So again, I like to write y equals x equals. And I just grabbed this problem from the web. I just did a Google search. Give me a good example of an interchanging orders of integration. It's a triangle. So x goes from 0 to 1. Here's 0, here's 1. And given a value of x, y goes from x to 1. Oh, okay. It means it's going to be this triangle. So initially, we fixed x. No, I'm sorry. I think I do this one. We fixed x, and y goes from x to 1. It's a triangle up here like this. So initially, we're going straight up. So almost surely, let's try going horizontally. So we need to figure out what's going to be the left bound of integration, what's going to be the right bound of integration. Well, this is particularly nice. What's the left bound going to be? 0. And what's the right bound going to be? So here we're fixing y, and then x equals, when we fix y, what will x be? No, 0. And now we fixed y, and now what does x equal to? Y. And so this is the same as the integral y goes from 0 to 1, integral x goes from 0 to y, e to the y squared dx dy. And you can possibly begin to see that this integral has been cooked up to be nice. So this is the same as the integral y goes from 0 to 1, e to the y squared. And then I have the integral x goes from 0 to y of 1 dx dy. I'm just trying to write it very slowly. What function has derivative 1 with respect to x? X. So when I integrate this, I have x. I evaluated x at y and 0. So what is the x integral equal to? It's just twice. I have the integral y goes from 0 to 1 of e to the y squared y dy. So this is almost perfect. Right? What am I missing to make this perfect? A 2. So if I put in a 2 over here and a 1/2, I'll go slowly and I'll do it with u substitution. So if I let u equal y squared, du is 2y dy, y goes from 0 to 1, u goes from 0 to 1. And so I love writing all of this stuff down over here. It makes it much easier for me when I substitute in, everything is there. I'm not trying to do anything in my head. Did it take a long time to write this down? No. When you are writing an exam, I have to pretend that I don't know math, but I can follow math. I can't guess what you mean. You have to put enough detail on the exam so that I know that you know what you're writing about. Do not just have math floating unconnected on the paper. Write what you're doing. We now do a u substitution over here, now we substitute. This way, if you make an algebra mistake, if you make a small error, if you've written down what you're doing and I can tell, oh, it's just a small error, you sometimes will lose no points. if I can't tell clearly what you're doing and why, I can't give you any partial credit. And you're more likely to make a mistake. So now when I section in, it's the integral u goes from 0 to 1, e to the u du. And what function has derivative e to the u? E to the u. So this would be e to the u, evaluated 0 and 1, so it's e minus 1. It would be 1/2, I got a couple. So the e minus 1 over 2. So approximately how large is e minus 1 over 2? E is approximately how much? 2.718281828. So E is about 2.7. Subtract 1, that's about 1.7 over 2. So that's 1 and so we want multiple. So if you have about 1.7 over 2, if I multiply by 5 over 5, so it's approximately 0.85. Let's look at the triangle. What's the area of the triangle? One-half. What's the largest either the y squared is on the triangle? E. So the largest the integral could be is e times 1/2. Oh, good. I've got e times that minus 1/2. That's not so bad. So this looks, pretty reasonable. Okay. So, this is an example of how you would do integration by parts. This is a little bit easier for me to hide, not integration by parts, interchanging orders of integration. But, again, you have a list of things to try. Can I change variables? Well, looking at this problem, it doesn't seem like there's a really good change of variables. I don't have polar, spherical, cylindrical. I don't have anything like that. The function e to the y squared doesn't have a nice antiderivative. So when I see something like this, my question is, what else do I have at my disposal? Well, I can switch the orders of integration. To do that, I have to very carefully write down what is the region. And in here, the region is going to just be a triangle. This is particularly nice because now we're going from 0 to y, rather than setting up from x and going all the way up to y. And when we do that, we get a little bit, and that's going to make things very nice. Okay. All right, any other questions on the material? Yes. Okay. So when you're trying to do the volume between two solids, there's two ways to do a calculation like that. You can view it as a three-dimensional integral, and you're just integrating over, say, all x, y, and z between the two solids. Or maybe there's a nice region in the plane that they both lie over. And then you go up until you hit the first one, and then you start counting, and you keep going up until you hit the second one. And when you do it like that, there's just a chart. And so when you do it like that, you're then integrating a two-dimensional problem of this height difference. And in some sense, it's really the same because you've just converted a z integral to be the height. So rather than writing it as integral of x, y, and z, I know, well, I'm just going to write the difference over there. So let's think of a good one to do. I'm just trying to construct something where the algebra is not going to be truly atrocious. So give me just one moment to try to. Okay, so let's look at, y equals x squared plus 1 and y equals 2x squared. So if I look at y equals 2x squared, it's going to be this bottom curve over here. If I look at y equals x squared plus 1, when x equals 0, it's going to be 1. When x equals 1 or negative 1, it's going to be equal to 2, the same value as the other. So these two parabolas will hit precisely at those points. Do we agree that this is a correct drawing of this? So now let me give you z is x squared plus y squared plus 1, and z is 2 x squared plus y squared. So I'm giving you two different surfaces, and I want to find the volume between them. So this is basically the volume between two paraboloids. Okay? And so what I need to do is I need to find which is the bottom, which is the top. Where are the intersections? So is this the bottom or the top? This is the top. This is the bottom. So where's the intersection? So z top equals z bottom. So x squared plus y squared plus 1 is 2 x squared plus y squared. So we have x squared plus y squared equals 1. So the intersection is going to be a circle of radius 1 centered at the origin. And so what I can do is I can view the circle in the xy plane, and then above each point on the circle, I start at z bottom and continue until I get to z top. And then if I integrate that over the entire circle, that will give me the total volume. So I would want the integral over x squared plus y squared less than equal to 1, z top of xy minus z bottom of xy dx dy. Do I want to do this integral in Cartesian? No. So I'll write it down a little bit more explicitly. It's integral x squared plus y squared less than equal to 1. What is z top minus z bottom? It should just be 1 minus x squared plus y squared. Right? Because z top minus z bottom, x squared plus y squared minus 2x squared, so I'll have a minus x squared plus y squared, and I'll have a 1. I could actually do some of this integration pretty easily. Which part of this integration can I do easily? So I have the integral of 1 minus x squared plus y squared dx dy. I claim one part of this integral is actually easy. Any thoughts on which? can you integrate the function 1 over the region x squared plus y squared less than equal to 1? If you integrate 1 over that region, what do you get? I'm sorry? Yeah, the area, right? If you integrate the function 1 over a region, it's just the area of the region. What's the area of the region x squared plus y squared is less than equal to 1? What kind of region is that? Yeah, it's a circle of radius 1, so it's just fine. So it's just pi minus the integral x squared plus y squared less than equal to 1 of x squared plus y squared dx dy. I didn't have to do this. I could have converted this to polar, but given that it's the nice function 1, I might as well just pluck that off. Now we convert to polar. And this is pi minus the integral. What is x squared plus y squared when we convert to polar? R squared. And what does dx dy become? R dr d theta. So theta goes from 0 to 2 pi, and then r goes from what to what? 0 to 1. So this is going to be pi. The theta integral is just going to be 2 pi. The r integrals, we have r cubed, so that becomes r to the 4th. And we evaluate r to the 4th at 1 and 0, so it's just 1/4. So we get pi halves. So does that look like a reasonable answer? Again, whenever you can check and see is the answer reasonable, you should always do that. Many of us, myself included, we are guilty of forgetting to check at times. What's the area of the disk? Pi. What's the maximum distance between the two surfaces? 1. So we know the answer can be at most pi. What's the minimum distance between the two surfaces? 0. So we know the answer is somewhere between 0 and pi. Oh, good, it's right halfway in the middle. Okay, that seems reasonable. Are you shocked that there is a pi that comes into play with the answer? Why not? Yeah, there's a circle. So as soon as there's a circle, and I have this beautiful symmetry, I can rotate the angle, I'm not too surprised that a pi comes into play. What if the answer ended up involving an e? Would you be surprised? I would be shocked if an e came into this problem. And I would think, I've got to have a long inside derivative somewhere if there's an e. Okay, any other questions on this problem? Yep. So if we chose to do it in x and y, so we're setting it up to do the x integration first. So what we'd do is we would fix the value of y, and we'd be going like this. So here are the two different regions. If x squared plus y squared equals 1, you get x is the square root of 1 minus y squared on this side. And what would you get on this side? It would be negative square root of 1 minus y. So we'd have the integral, x goes from negative square root of 1 minus y squared to square root of 1 minus y squared. Y goes from minus 1 to 1. And then x squared plus y squared dx dy. And you can try to do that integration. Given that I have an x squared, when I integrate that, I'm going to get an x cubed. So I'm going to get this to a 3/2 power. That's not going to be pleasant. But the final answer is nice, so perhaps there is a way to make the integration work. It's going to take some effort, but okay. Any other questions on this?
Is there a reason why you didn't use spherical coordinates?
Yes, because it's not a sphere. So I have two paraboloids. Those are not spheres. I don't have things involving x squared plus y squared plus z squared being constant. I have things that only depend on the value of x squared plus y squared. So when I'm trying to figure out what's going on, I have two paraboloids, and if I look at their intersection is a circle. And that's what I was trying to draw up here on the top board. You're looking at just the lower dimensional analog rather than having z equals x squared plus y squared plus 1, looking at y as x squared plus 1. And I'm really replacing y with z and replacing x squared with r squared. And so I'm really just now rotating it by 2 pi, and that's why it's sweeping out and becoming circular. This is really an example not of spherical coordinates, but of what coordinates? If you want to view it as 3 variables, what coordinate system would it be? Cylindrical. And I'm basically just hiding the z integral. You could write the z integral is z goes from z bottom of xy to z top of xy, 1 dz dx dy, and we'll have x squared plus y squared plus equal to 1. Or we could do things in polar. And then it's just, we know what the integral of z of 1 with respect to z is. If I want to integrate 1 with respect to z, I just get z, and it's going to just be z top minus z bottom. And so in that situation, we might as well just integrate not 3 variables, but 2 variables and just use as the integrand of the height. So if we do it like this, it's a 3-dimensional integral. If we do it like this, it's a 2-dimensional integral. Here, the integrand is the height. And here, instead of having the height, you just put a 1 for every point inside the region. And when you add up the contribution from all the points inside the region, it gives you the volume. Does this answer the question?
Yep, thank you.
Okay. Any other questions on this? All right, so the last question was on TaylorSeries. And so the question was, talk about the radius of convergence and Taylor series for functions with 2 and more variables. So we really haven't talked too much about when does a Taylor series converge with several variables. We've really only talked about the convergence of a Taylor series for functions of 1 variable. What you could do if you have functions of several variables is you could group things of the same degree. I want all terms such that the power of x times plus the power of y is equal to 1. All the terms where the power of x plus the power of y is 2. All terms where the power of x and the power of y add up to 3, and so on. And then for each one of these, figure out what is your maximum contribution, and then reduce it almost to a 1-dimensional problem. So for us, we really care about trying to understand a 1-dimensional Taylor series. When does it converge? So t infinity f of x would be the sum, and goes from 0 to infinity, the nth derivative of 0 over n factorial x to the n. So the question is, what's a good test to use for this? So one thing you have to be careful about if you try to do, for instance, the ratio test, you might have a situation where one of the derivatives is 0, and you don't want to be dividing by that. So what might be a better test to use here? I'm sorry? So if you want to do the integral test, you would have to come up with a function where you replace the nth derivative at 0 and n factorial with a function of x. And that's going to be challenging. Could do comparison, root test. Yeah. Is it easy to take the nth root of x to the n? Yeah, and we know n factorial is approximately n to the n e to the minus n square root of 2 pi n. So the nth root is approximately n over e. Because the nth root of 2 pi n is just goes to 1. So if we look at x to the n over n factorial and take the nth root of that, that goes to x divided by n over e, so it becomes ex over n. What do you know about ex over n? What happens to that as it goes to infinity? Goes to 0. So this is going to 0. So when I'm trying to understand convergence, this is only growing polynomially. This is decaying, faster than exponential. It's decaying like n over e to the nth power. This has tremendous decay. Why might this have trouble converging? I mean, we've got x to the n over n factorial gets very, very small. What's the only thing that could prevent this from converging? Yeah, if the nth derivative is doing what? If it's increasing, it's got to be more than just increasing. It's increasing extremely fast. What if the nth derivative, imagine that equals n to the n. Okay, that's increasing faster than n factorial. If that was the case, then when we did the nth root, we would have n to the n, x to the n over n factorial to the 1 over n. That would be approximately n ex over n. Which is ex, which does. So for what values would this converge? So this is my rho. The rho equals the limit and then goes to infinity. For what values of x would this converge? Yeah, so this converges if x is less than -. And so if the nth derivative is going as fast as n to the n, it's still going to converge. With much, much more restricted range. What if instead we knew that the nth derivative, let's say, is less equal to n to the 3n over 4. So 3n to the 4 is still quite large. Yeah, this is going off to infinity very rapidly. How do you think that compares to the n factorial? The n factorial is like n over e to the first is the n. This is n to the 3/4. So if you want, you could even do this as n to the n divided by n to the n fourths. We still have the e to account for, so let's look at what happens. So rho would be the limit as n goes to infinity of n to the 3n over 4 x to the n divided by n factorial. This is approximately the limit as n goes to infinity. Well, and this is taking the 1 over n power. Well, n to the 3n over 4 to the 1 over n is just going to be n to the 3/4. We'll have x, and then n factorial to the 1 over n. We said n factorial to the 1 over n is about n over e. So this is equal to the limit as n goes to infinity of x divided by n to the 1/4. And so what is that going to be? So n goes to infinity, what is ex over n to the 1/4 go to? 0. So if we're in a situation where the derivative, the nth derivative at the origin, is growing slower than n to the 3n over 4, this Taylor series will converge for all values. That's tremendous growth. If you take your function as sine or cosine, what can you tell me about the derivatives of sine and cosine anyway? They're never going to be less than -1, and they'll never be greater than 1. So the derivatives of sine and cosine are always at most 1. So when you look at the Taylor series of that, it's going to converge. What if I gave you e to the x squared? I could try to figure out what the derivatives of this are at the origin, right? And try to just see how quickly they grow. There's a faster way, though, to find the Taylor series of e to the x squared. Does anybody know the faster way to find the Taylor series of e to the x squared? What? Yeah. We know what the Taylor series of e to the u is. So this is my favorite trick. I don't know why it's not taught nearly enough, but we know e to the u is the sum, n goes from 0 to infinity, of u to the n over n factorial. Let u equal x squared. So then e to the x squared is just the sum, n goes from 0 to infinity, of x to the 2n over n factorial. And you can show that that converges for all values of. All right, so I think this is a good place to stop. If we do different types of problems in the second section, I will let you know. So the question is, how much time will we have on the exams? It will be last time plus 10. Correct. And the exam will be broken up so that you will be getting feedback after the first part before you have, after the second part before you have to do the third part. I am not splitting the topics so that everything is fair game on Monday. And this way, if you do have any misconceptions, you can fix that before the rest of it on Wednesday. All right, have a good day, all.
Professor?
Yes.
Is the take-home exam untimed?
The take-home is untimed, closed book.
Okay, thank you.
Yep, and it is due at the start of class. It is not accepted late.
Okay, thank you.
Yep, you're welcome.